Welcome to Introduction to Graph Theory. In this lesson, we will define graphs and also define common graph theory vocabulary. In the modern world, planning efficient routes is essential for business and industry, with applications as varied as product distribution, laying new fiber optic lines for broadband internet, and suggesting new friends within social network sites like Facebook. The field of graph theory started nearly 300 years ago as a look into a mathematical puzzle called the Seven Bridges Problem. The field has exploded in importance in the last century, both because of the growing complexity of business in a global economy and because of the computational power that computers can provide us. As an example, consider a police officer patrolling a neighborhood on foot. The ideal patrol route would need to cover each block with the least amount of backtracking or no backtracking to minimize the amount of walking. The route should also begin and end at the same point where the officer parks his or her vehicle. We'll use this example to cover some of the basic graph theory or network analysis vocabulary. A graph is a finite set of dots and connecting links. The dots are called vertices or nodes, and the links are called edges. A graph can be used to simplify a real-life model and is the basic structure used in graph theory. So this is a diagram of the neighborhood the officer must patrol. We could use this graph to represent this model. Notice how each intersection would be a dot, which we call a vertex, and each street would be an edge in the graph. Notice how here we have 6 vertices and 8 edges. So again, a vertex or node is a dot in a graph where edges meet. A vertex could represent an intersection of streets, a landmass, or a general location like work or school. Note that vertices only occur where a dot is explicitly placed, not wherever two edges cross. Looking at this graph here, notice how we have two edges that cross, but because there's no dot, there's no vertex here. As an example, imagine a freeway overpass. The freeway and the side streets cross, but it is not possible to change from the side street to the freeway at that point, so there's no intersection and no vertex would be present. Normally we use capital letters for the vertices as we see here. Edges connect pairs of vertices. An edge can represent a physical connection between locations like a street or simply a route connecting the two locations like an airline flight. Edges are normally labeled with lowercase letters as we see here in blue. So again, we use capital letters for the vertices and lowercase letters for the edges normally. Now, depending on the problem being solved, sometimes weights are assigned to the edges. The weights could represent the distance between two locations, the travel time, or the travel cost, or several other possibilities. It is important to note that the distance between the vertices in a graph does not necessarily correspond to the weight of an edge. So looking at our graph here, notice how edge AF and edge CD are the same length, but their weights are different. So graphs do not have to be drawn to scale. So it's important that we pay attention to the weights of the edges when they're given. A loop is a special type of edge that connects a vertex to itself. So looking at this graph here, this would be a loop from this vertex. Now the degree or valence of a vertex is the number of edges meeting at that vertex. It is possible for a vertex to have a degree of 0 or larger. So here are several examples. Here's a vertex with degree 0, degree 1, degree 2, degree 3, and degree 4. A path is a sequence of vertices using edges. Usually we are interested in a path between two vertices. For example, a path from vertex A to vertex E. So one possible path from vertex A to vertex E might look something like this. But of course there are several other paths from vertex A to vertex E. For example, this would be another path from vertex A to vertex E. And of course there are others. A circuit is a path that begins and ends at the same vertex. So starting at vertex A, we can form several circuits. For example, we could go from vertex A to vertex B, to C, to D, to E, to F, and then back to A. Another circuit might be from A to B, to E, to F, back to A. This is another circuit containing vertex A. A graph is connected if there is a path from any vertex to any other vertex. So this first graph here is connected because if we start at any vertex, let's say this vertex here, and then we select another vertex, let's say this vertex here, there will always be a path from this vertex to this vertex or any other two vertices we decide to select. One possible path would just be like this. But the graph on the bottom here is disconnected because there's no way to get from the vertices on the left to the vertices on the right, meaning there's no path from, let's say, this vertex to this vertex because this graph is disconnected. So to finish, let's go back to our opening example. A police officer is patrolling a neighborhood on foot. The ideal patrol route would need to cover each block with the least amount of backtracking or no backtracking to minimize the amount of walking. The route should also begin and end at the same point. Let's see if we can find a route with no backtracking. We first need to decide where the patrol officer was going to. We would first need to determine where the we would first want to determine where the officer is going to park the car. For example, let's say the patrol officer parks at vertex A. Let's see if we can return to A by using every edge once and only once. We could go from A to B, then B to E, then E to B, then from B to C, C to D, D to E, E to F, and finally back to A. Notice how we started and ended at A, and we used each edge once. Therefore, we did minimize the amount of walking the police officer had to do. In fact, the police officer had no backtracking. This is actually a special type of path that we'll talk about more later. A path that uses every edge in a graph with no repeats is called an Euler path. I hope you found this introduction helpful.